Good morning, everyone. So today's Friday, April 24th, so we're one class past the midterm. So we're going to jump back into lecture today. We're still in Chapter 5. We're going to be doing some more MOSFET examples. And then now we are slowly going to be turning our attention to building or designing amplifiers from MOSFETs. And that's going to take up a big chunk of the next week or so, next 2 or 3 lectures. And then that'll close out Chapter 5, and then we'll jump into BJTs and a couple final topics as we reach the end of the semester here. One quick note, I'm going to start working in some lecture materials from 2019, from spring 2019, just because I think they're a great resource, and there's really no replacement for speaking in front of the class and in front of an audience. So you'll start to see some older clips worked in with some of the newer stuff. But I have done editing to make sure that it all comes together pretty nicely. Anyway, I will talk to all of you on Tuesday, and hope you're doing well. Good luck. Bye.
Good morning, everyone. We're still in Chapter 5. We're going to pick up where we left off. I'm not going to do too much of a review this time because we were going through examples and there's really not too much to backtrack to. The most logical starting point, just to jump right into the next example, which is 5.7. So a couple things that I wanted to say right off the bat here. I did say, and this is still true, that you will not be asked to do a mathematical calculation-based PMOS problem on a quiz or an exam. The reason why I set that constraint or limitation is because I wanted to reduce the amount of material that you need to really study, and I do want you to repeat, the NMOS enhancement type transistor problems. That being said, this is still an important problem to pay attention to for 2 reasons. I still can ask PMOS or depletion type transistor problems on a quiz or an exam as short answer questions. Okay, and so what that means is you need to understand still how they work, and so understanding this example 5.7 I think will enhance that understanding. So we're going to go through this. I know that this is not something that I said explicitly in this form could show up on a quiz or exam, but it's still important. So we want to design the circuit shown here such that the transistor operates with a throughput of 0.5 milliamps and a value of VD, that's 3 volts. And this is an enhancement type PMOS transistor. It has a threshold value that's given here, -1 volts. And then this is the device transconductance parameter. We assume that lambda equals 0. What does that tell us? Again, that we're not considering channel length modulation. So we can ignore that. Okay, so the question is, what is the largest value that RD can have while maintaining saturation region operation? So if we imagine we're looking at the graph here, initially we're somewhere in this region. We want to figure out what value of RD takes us to right there. Okay, so first thing, step number 1, what is the constraint that signifies the boundary between the triode and the saturation regions? And for this, I didn't originally have it in the slide, but you can see I wrote it in. I went to table 5.2, which is at this point slide 68 in the lecture notes. That can always change because we insert or delete something, but you can see there's several equations that we can use to signify the boundary between triode and saturation. So these two inequalities, this one and this one, actually define the boundary. So when VDG is less than the threshold, the absolute value of the threshold voltage, we are in saturation region. Or alternatively, and this is an equivalent statement, when VSD is greater than the overdrive voltage, we are also in the saturation region. Now this equation here is not an inequality. It's not a constraint. It is defining VOV for this PMOS case. So for example, you would have to use this third equation in order to understand the second. So I just wanted to lay all those out there. We'll come back to them in a second. Now, next we want to solve for the overdrive voltage, which satisfies this constraint right here. And so we know that we're going to have to use this type of equation. We know that we're in the saturation region, so ID will be equal to 1/2 Kp prime aspect ratio VOV squared. You'll note that this is the same for both the NMOS and the PMOS, as long as we define it in terms of the overdrive voltage and not in terms of VGS or whatever. Because if we were to actually make a substitution, what we would see here is that this is VSG minus the absolute value of VTP squared. That's what we would substitute in right there. But we can do it in terms of VOV. Anyway, so going from here to here, we're going to solve for VOV. And essentially, what we know this, we know this, we know this, we know this. The length, the width, the transconductance parameter, we know the throughput current. And so we can go ahead and solve for a value of 1 volt as the overdrive voltage. Now, we're going to, like I showed a second ago, take this equation right here. And so now we're going to work backwards to get the value of VGS that's associated with our VOV. So this is 1 volt. This is minus 1 volt. We go ahead and solve everything, including the absolute values. And what we see is that the value of VGS that puts us at, again, the boundary between the saturation and the triode regions is going to be -2 volts. Okay, so that's an important part of this problem. Next, what value of VG satisfies the constraint from the problem statement? So all we're doing now is we came up with the value of VGS that's desired. Now we want to come up with the value of VG that is desired. So let's go back here and look at the circuit for a second. All right, that's going to help us solve for actually multiple values. So let's go back here. Okay, so let's figure out what VG is based on VGS, which last slide we said this is -2, and VS is 5. How do we know that? Let's take a look over here. How do we know that VS is 5? The reason that we know that is because this has already been defined as the drain. This is therefore defined as the source, and so this is equal to VS right here. Okay, so our value of VG is 3 volts. Next, and so we're sort of doing this a little bit out of order, but it's still a relevant way of looking at it. Okay, so we have VG, which is 3 volts, and now what we want to do is we want to come up with the values of RG1 and RG2 that satisfy that value of VG. Again, this is going to act like a voltage divider because we don't have any current flowing in that direction. This current equals 0. And so what we can say is that VG is equal to VDD RG2 over RG1 plus RG2. This is a little bit of a sidetrack. I don't know if it explicitly asks for this in the problem, but I went ahead and solved for it, so we'll go ahead and do that. So we apply our voltage divider. We know what this value is, and so we can go ahead and go back and solve. So essentially what it tells us is the ratio between RG1 and RG2. So if we assume that RG2 is 3 mega ohms, then we would end up with an RG1 of 1 mega ohm. This whole piece of it right here is not explicitly asked for as an answer, so I'm not sure if we really had to do that, period. But let's jump back to the main part of the problem, which is to figure out RD. And so finally, let's solve for what they actually did ask for, which is RD. So how do we solve for that? We know that VD min will be equal to VG plus VTP. Now, how do we know that? That's taken from these expressions right here. And so we plug in the values that we know. We know that VG, goes back here, is 3 volts. We know that this is 1 volt. And so that gives us a VD min value of 4 volts, which we then divide by our 0.5 milliamps, and we get 8 kilo ohms right here. So that's the maximum value, and this should be absolute value, I apologize. And so that gives us the value of RD max. So anything larger than 8 kilo ohms will push our PMOS transistor down into the triode region. Okay. Next problem, exercise 5.8, a CMOS transistor. So this is a really interesting problem. Again, so the CMOS is NMOS plus PMOS. So we have both types here. Again, same disclaimer about the types of problems you could see on an exam. I guess given my rule, it would exclude this specific type of problem from being asked, but it's still a really good problem to go over, again, for the short answers and for more other types of questions that I might ask. Okay, so let's jump in here. Again, CMOS stands for complementary metal oxide semiconductor field effect transistor technology. Okay, so the NMOS and PMOS transistors in this figure here are matched, meaning that they have the same device transconductance parameters, both of them 1 milliamp per volt squared. The thresholds are the same, so VTN equals 1 volt, and our VTP equals negative 1 volts. It asks us to find the drain current IDN as well as IDP and solve for V out when we have these three different cases, 1, 2, and 3. All right, so the first thing that we want to do is to calculate VGS for both of the transistors. And we're starting off with the case where VI is equal to 0. Now, I have here VGS equals 2.5 volts. How do I know that? Okay, if the transistors are matched, actually, it tells us right off the bat because we can see here this voltage VGS is 2.5 volts. This voltage VGS negative 2.5 volts. So both of these values come directly from the figure. Next, determine the status of both transistors, blocking versus not blocking. And so for that, we're going to use the constraints that are taken from table 5.1 and table 5.2. This is for the PMOS, and this is for the NMOS. Okay, and so what we see is, right, it's all laid out for you. If this occurs, then we're blocking. If this occurs, then we're in triode. If this occurs, we're in saturation. And so both are not blocking. And so how do we know that? Let's try to spell out these inequalities. So over here for the PMOS, VSG would equal to positive 2.5 volts. Is that less than the absolute value of 1.0 volts? Okay, no. So we know we're not blocking. And then let's do the same thing for the N-type. VGS is equal to 2.5 volts. Is that less than VTN? Again, no. So we know right off the bat that they are not blocking both of the transistors. Okay. So now, because the transistors are matched, their resistances are equal with the same biasing. This is a problem where there is a little bit of a shortcut. If the transistors weren't matched exactly, we'd have to do a little bit more work. Because they are matched and they're biased in the exact same way, 2.5 volts, they have threshold voltages with the same magnitude. So because that's the case, we know that this resistance here, I'll call it Rx, and this resistance here, Rx prime, they are equal to one another. And actually what I did was I called it Rfet. You can see down here I called it Rfet. So if we represent the circuit shown to the right with matched transistors, we can replace them with matching resistances. We may not know what the resistance value is, but we know it's the same. And then we can define V out by applying KVL to this circuit. So this expression right here is an application of KVL. And so I recommend that you take a look at it. It's pretty straightforward, right? 2.5 minus VO over Rfet. That is telling us that the current flowing here will be equal to the current flowing here, which is V out minus a negative 2.5, plus the current flowing down the side branch, which is V out over 10 kiloohms. So you can see here that I was very careful to match the current values. We have IDP, IDN, as well as IO down here. And so what we see, once we complete the algebra, we end up with a value of V out equals 0. And this makes sense given what we know about the way that matched transistors work anyway. If the same voltage is applied across both of them, the midpoint will be the total voltage divided by 2. So we have 5 volts divided by 2, shifted down by 2.5 volts, and so we end up with 0. Okay, now we need to find next what is the value, because they want us to find both the drain current for both of the transistors. So we need to work backwards. So do they tell us that we're in the saturation region? No, we're going to assume that we're in the saturation region for the moment. Although you should be able to figure that out right off the bat. Right, if we go back to the first slide here, is VSG greater than VTP? It is. So we're in saturation. Same thing down here. So actually, on the first slide, you can see that we're in saturation region. And anyway, so we apply this equation for the transistor in the saturation region. We work backwards. We calculate what our V, actually we know what VOV is. We go ahead and calculate our IDP, and that gives us 1.125 milliamps. And then you could do the same thing for IDN and V out. So this problem, I gave you the beginning, and then I asked you to sort of run with it on your own after that point. Okay, this is homework number 13, usual drill. It's technically due a week after it's assigned, so this is the lecture for Friday, April 24th. So I'll ask that you take a look at it, and obviously now the only thing that's left is the final exam. So everything that we go over from this point forward is going to be on the final exam. So that's really what you're looking forward to. Okay, there's a couple of homework problems that are in the actual lecture notes. These are some homework problems that were especially difficult, and so I decided to include in here. So we're going to go ahead and include them as part of the lecture. So homework solution 547. The transistor shown here has a process transconductance value of 0.4 milliamps per volt squared. a threshold voltage of 0.5 volts, and a lambda equals 0, so no channel length modulation, show that operation at the edge of saturation is obtained when the following condition is satisfied. So this is a problem where they tell you what the answer should be. They just want you to show it. So show that the following statement applies for the edge of saturation. Okay. Step number 1. We define the inequality constraint for the edge of saturation, which we know all too well by this point. VDS is greater than, or actually we're looking at the edge, so it would be equal to VOV. All right, let's fill in the values that we know. We know what VGS is, okay? It's 1.8 volts, because that's the difference between this point and this point right here, so that we know. We also know VT, because that's given to us as 0.5 volts. All right, so we know that our VDS is going to have to equal to 1.3. So we need a 1.3 volt difference right here in order to reach the edge of saturation. Okay, we can also see that KVL will apply to this circuit as it does always. So what we're doing from this point forward is we're laying out the equations that we need in order to solve. VDS is equal to VDD minus the drop across the resistor. And IDS, we're going to assume that we're in the saturation region. Well, actually, it's not an assumption because they tell us that edge of saturation. So this is good. So we can take this value and we can essentially plug it in right there. And then set this all equal to 1.3 volts, right? Because we get this value up here, we can use it down there, and then we have our IDS and we can use it up above. So everything comes together on this slide. All right, so you can see this is the combined version of the expression. And what we are trying to do is solve or show that this applies. And so, so how does this go from becoming an equality to an inequality? What we do is we are going to replace our value of VDS with this right here. So that's the reason why it goes from being equal to VDS to, and then below, now it's all of a sudden greater than VGS minus VT, because we made that substitution right here. So we make that substitution, we plug in the values that we know, and we solve down. I don't know if it's really worth it to go through every single step of the derivation. And, essentially we end up with what we were expecting, which is that the aspect ratio times RD has to be greater than 1.5 kiloohms in order to satisfy this equation right here and stay in the saturation region and be at the edge of the saturation region. So what that means is if the product of these three together grows larger than 1.5 kiloohms, then it will move down into the triode region. So, this is really the last major topic that we're going to talk about as far as MOSFETs are concerned. And it's still a major one. It's going to take us probably a class or two to get through it, at least the rest of this class and all of next class to get through it. But how to make an amplifier. And this is, I don't want to say the culmination of this class because there's a lot of different purposes, to taking ELC251, but it's definitely one of the big parts of it. Going from only having, an understanding of linear circuits and passive elements, with the exception of amplifiers, to being able to design the very most basic transistor device, which is the amplifier. We're not going to make the world's best amplifier. It's not going to be as good as even something real cheap like the 741, but it'll provide amplification. Okay, so we have already talked about how we can look at the MOSFET when it's in the saturation region, we can look at it as a voltage-controlled current source, where the current source behavior is between the drain and the source. This is essentially where your current source would be, and the voltage control is your VGS. Okay, so how can we translate a voltage-controlled current source into a voltage-controlled voltage source? That's all really an amplifier is, right? An amplifier is a voltage-controlled voltage source where we can have some sort of manipulation over what the coefficient is between the input and the output. So already, without doing anything, this makes a pretty good transconductance amplifier. But we want a voltage amplifier. So how do we do that? We add an external source and a resistor. And so originally we had control over ID. Now we have control over VDS, which is the voltage output. If you think about this as an amplifier, you can think of this as the input, okay? The signal that we're going to be amplifying, and the output is going to fall between those two terminals. So input is inside of here because VGS will have an effect on ID. Output is here, which is our VDS. All right, so what does that VI relationship look like? So let's say I were to graph, and I have the graph here. Let's say I were to graph VGS versus VDS. What would that relationship look like? So on the x-axis is the quote-unquote input, the value we're trying to amplify. And on the y-axis is the output, the amplified value. What would be the best? The best would be if it looked exactly like this. Right? That would be great, because then our gain would just be the slope of whatever that line is. And this is the type of a relationship you have with, like your 741s and all that type of stuff. But as you can see here, right, that's not the case. The input-output relationship is more nonlinear. And so there's three different regions that we can essentially talk about. And what we're going to do is move from left to right along the x-axis. So first things first. When VGS is 0, up until when VGS is equal to VT, the overdrive voltage is 0, right? That means that the switch is completely open. There's no current going to be flowing. And so the output here, this voltage will be equal to this voltage, right? When VGS is less than VT, the circuit is open, no current flowing, no voltage drop across this resistor. This voltage equals that voltage. So for very small values of VGS, that's why you see here VDS equals VDD. Nothing's happening. Next, then we enter the saturation region. Why is it going to be the saturation region? Because initially the value of VDS is going to be really big, right? VDD most times is going to be 5, 10 volts, okay? So initially VDS is really big. It's bigger than VOV, and we're in the saturation region. Now what happens as we continue to increase VGS? As we continue to increase VGS, the switch, if you think about the transistor as a switch, the internal resistance is getting smaller and smaller. It's closing more and more, okay? And so if we go back to the circuit, this allows more and more current to flow through between the D and the S terminals. More current flowing this way, bigger voltage drop across RD, which means that you would expect that voltage to go down, right? If I were to draw here on the board the same sort of graph that is in the notes, this is VDS. If I were to draw ID, no, actually that shape's not exactly right. I'm just going to draw it linearly. It'll go up. It'll increase, right? So the more that the current increases, the more that the voltage VDS will continue to drop. What happens right here, eventually VDS will get smaller, it'll get smaller, it'll get smaller, and it will reach the point of being equal to VOV, right? Yes?
Why is VDS dropping?
VDS is dropping because as you increase VGS, that's the equivalent of closing the circuit, making the internal resistance between these two terminals smaller and smaller, which means more and more current will flow down here. What is this voltage? VDD minus ID times RD. As ID gets bigger and bigger, VDS gets smaller and smaller. Eventually, we'll get to the point where VDS is equal to VOV, and it'll switch over from saturation into triode, and then we get the rest of it. It'll continue to close, the current will get higher and higher and higher, and then eventually the current will get so high that there'll be no voltage left across the DS terminals. The drop will all be across RD. So if you look here, the red bullets, those are just the different equations we use in the different regions. It doesn't say anything you haven't seen before. For all of the different regions, V out equals VDD minus ID RD. That works here, that works here. It also works here. Although because ID is 0, we can leave out the second chunk. VDS is, this should be less than VOV. Can I fix that here? Okay, VDS is less than VOV when we're in triode. VDS is greater than VOV when we're in saturation. And over here, I put VDS as question mark VOV. The only reason why I say that is because when it's in cutoff, there really is no overdrive value. Remember, we said that the overdrive voltage can't go below 0. So in this region, the overdrive voltage is actually undefined. Okay. This equation here, this is the ID, the VI relationship for triode region. This is the VI relationship for saturation region. And in the cutoff, ID is equal to 0. And then this is always the same. Overdrive voltage is VGS minus VT. Okay? So, not really any new material in those bullets, but I wanted to, because when we do these amplifier-based problems, sometimes it helps to have everything in one spot. So what we have here is there's two different cutoffs that we have to worry about. There's the cutoff of the FET, and that's when the FET completely opens up and doesn't allow any current to flow. And then there's the cutoff of the amp, which is when the voltage drops to 0. And that's the opposite. There's so much current flowing that the voltage VDS has dropped down to 0. So there's a sort of an inverse relationship going on there. The amplifier will be putting out the maximum voltage when there's minimal current, when the amp is opened up, and then vice versa. Okay. There's a couple of important points that we can define. One of the important points, so let me give you a preview. And I think I've already said this. The amplifier is going to be operating in the saturation region. So point A and point B are really important. Because if we're defining how this thing is going to work, we need to figure out component, parameters, inputs, whatever else we're going to be defining. We have to make sure that that maintains operation between here and here. How do we know where A is? A is pretty easy because A is just going to be where VGS is equal to VT. That's an easy one. Point A is easy to define. Point B is not necessarily so easy to define. It's the transition between saturation, which is here, and triode, which is here. And so there's two equations we can use to calculate that. 532, well, 532 is an equation you've already seen, and then 533. So all this is saying VDS equals VDD minus ID times RD. We've used this equation a million times. We know we're at the edge of saturation in triode, so we can use either one there. We'll use the saturation region equation. And now we go back and we solve for our value of VGS. And so what we see is that the value of VGS right here at point B, and this is the point at which VDS is equal to the overdrive voltage, we can use this equation. And that's just an inversion of what's shown above. So when we're talking about using the amplifier, we need to stay between point A and point B. We need to stay between VGS is equal to VT on the low end, and then on the high end, we need to stay below this, where VGS is equal to this value, given by the equation. All right? Now, what I'll stop and close on is that we don't want to use the whole range between A and B. We want to use a smaller range within there. So A and B are sort of like the absolute maximum value. It's like the two edges of the road. You could be driving on the edge of the road and still not be doing a good job, but the edges are the absolute boundaries for where we do not want to pass. And then we'll narrow it down from there.